All right, hello and welcome to the first of 6 videos about computer programming. So, if you got an interest in computer programming, this is a good time to be alive because computer programming is absorbing more and more of what we experience every day, and we're just on the cusp of some amazing things that are going to be accomplished through computer programming and software, like self-driving cars, self-flying planes, etc., etc. There are a lot of things um, in computer programming that are just fascinating, really cool exercise of your mental ability. So even if you don't intend to make it an occupation, it's a really cool hobby for a lot of reasons. So anyway, this will be the first of 6 videos, and we're going to talk about general computer programming principles in the first two. In 3 and 4, we're going to apply those in a programming language called Python. And in 5 and 6, we're going to apply those in a programming language called Java. So those are two languages of many, and they all have pros and cons, but Python and Java are two of the most commonly used. So it's a great starting point. Most programmers specialize in one language, not all, but very few people know more than a few, at least well. Okay, so anyway, general coding principles. So the first question is, what is the difference between computer programming and coding? Those are interchangeable terms. They mean the same thing. So a lot of times you'll hear it referred to as coding. A lot of times you'll hear it referred to as computer programming. Those are interchangeable terms. They mean exactly the same thing. So don't get confused by the use of them interchangeably. All right, so what is programming? Well, it's providing a set of instructions. Now, typically computers are what we program, but you can create an algorithm to solve a problem for a person too, or anything. So, for example, if I were going to explain to you guys how to change brakes on your car, I would give you some very simple general instructions. Take the wheel off, take the caliper off, switch the pads, put the caliper back on, etc., etc. So I would give you these very general directions, and you would fill in the details because you're smart. But computers are not smart. In fact, they're dumb, very dumb, and they can't figure out those details. So we have to provide all the details for a computer for it to work. So our instructions to a computer have to be extremely detailed, and they have to be written in a way that even a computer can understand it, which is pretty complex, as you'll see later on. So providing the computer a set of instructions that are written in a language that the computer can understand. So computers speak a certain language by default at the CPU level, and I'll get into that a little more later, but the programmers, the higher level programming languages that we're going to learn are filtered through an interpreter and then rewritten into a language the computer can understand and then fed into the CPU. So there are layers of complexity to computer programming. And often as a computer programmer, you'll type up a big program and then it'll fail and you're not really sure what's going on. You've got to debug it. And then sometimes you're surprised when it works as well. So that's what that little cartoon's about. So why do you program computers? Well, they're fast, they're cheap, especially fast where mathematics is concerned. You know, mathematical calculations are virtually instantaneous on a computer, and if you try to do those manually, they would take forever. So fast, cheap. You know, computers aren't very expensive nowadays, especially. Many years ago, they were more so, but they're still relatively very cheap for what they can do. And they're inexhaustible. In other words, they can go and go and go like the Energizer Bunny. They just go forever. And so they perform significantly better than a person for repetitive tasks that can be coded into a set of instructions. So here's an example of a old school computer program in a Commodore 64 that just goes on forever and creates these random lines that makes an interesting maze-like shape. The computer can do this forever. It's never going to ask for a paycheck. It's never going to ask for a smoke break. It just goes on and on and on and never stops. So that's why you would bother to program a computer. Excuse me. So everybody's got an anecdote that is a hobbyist computer programmer like myself, you know, of themselves as a kid sitting in front of a computer making the first video game or whatever. So, my name is Chad Salyer, and I am a computer science teacher here at Elizabethton High School. I've got a bachelor's in mathematics from ETSU and a master's in educational leadership from ETSU. And I've been a computer programming hobbyist for a very long time, since the early 80s. So I've always had a little computer around and I've always tinkered with it, at least at the hobbyist level, to create my own little programs and so forth. So when I was a kid, I was into, working out, and I would make a little program that kept track of the weights I would use on a certain day and so on in my weightlifting. And also had programs that would keep track of my stats when I played baseball and so on. So I would make all those things, and a bunch of little rudimentary video games that are, pretty simplistic by today's standards. But back then I thought I was really doing something. Um, so most people have that kind of background that are in my age group that are computer programming today. We cut our teeth on this early PC generation of computers, which we're going to talk more about later. They were the first ones to accept standard basic computer programming language input, or some of the earlier ones, I should say. So you might ask, how do I code? How do I create a computer program? Well, first of all, um, you're going to develop a plan. So this involves no actual coding whatsoever. You're just either drawing out notes, or just thinking in your mind, what do you want to do? What task do you want to solve? And how can I break this down into steps that the computer will understand? So you're working through it mentally, thinking about what you want to do. And then you use a text editor, or IDE, which stands for Integrated Development Environment. And what an IDE does is it is another layer that removes you from the raw code. So you've got the assembly code, which is the CPU, what the CPU understands. And then you've got higher tier programming languages like HTML or Python or Java. And they give you a more human-like language, instead of assembly code, which is hard to understand. It's more removed from the way we speak normally. Higher tier programming languages are closer to the way we speak, and so they're easier to just understand by looking at. And then IDEs are another level that you drag and drop things, and it writes the code for you, for example, in some IDEs. And I'll show you examples of all those before the end here. Okay, so the interpreter is where that language is turned into the language the CPU can understand. Then it's fed into the CPU, and the CPU then processes it in whatever way is appropriate given the instructions you've given it. And it's going to give you some output, probably, or whatever you asked it to do. As long as your language is correct, it will accomplish that task. So you see on the left, I got pictures of guys thinking about it. And here he writes the code. Here he runs the code through an interpreter. And all this, so after this point, this is all the computer taking care of it itself. The computer interprets it for you, feeds it into the CPU, and shows you the results. So milestone.
All right, I wanted to run through a quick example of constructing a program using those steps we talked about. So you got planning, coding, then sending that code to an interpreter, then to the CPU, then you get your output. So let's imagine we want to create a BMI calculator. So if you look it up on the internet, which you would have to have this information first, the BMI calculator is M, where M is your weight in kilograms, divided by H squared, where H is your height in meters. So just planning, I know I'm going to need to do a few things. So I should have code that introduces the program. I need to ask the user for the stats. Now, the problem is the weight is in kilograms and the height is in meters. Not a lot of people in America are going to know their weight in kilograms or their height in meters. So let's ask the user for those in more standard measures and then do a conversion. So then we're going to need to, once we get the stats, we're going to convert those to metric, which is kilograms and meters. And then we're going to perform the calculation for BMI, and then we're going to output that to the user. So this will be my plan. Let's break this up into steps here. Code that introduces the program. Okay, that's one step. Ask the user for stats, and this will be two parts. So we need their weight in pounds and their height in inches, let's say. Convert those to metric, and then calculate the BMI, output that to the user. So those are the steps we're going to use, and each of these should represent about a line of code, sometimes more than that. So first step, second step, and that's really 2 part A and 2 part B, I guess. And then 3, 4, 5. So we need to complete these 5 steps in order to have a BMI calculator. So, and in order to code those, I'm going to use an online resource called Replit, and you're going to see me use that a lot throughout the course of all these videos because it's just so handy and it's free. So, and it's pretty user friendly. All right, so let's go to that Replit, repl.it, and you have to make an account, but it is free. Okay, so accomplishing our task. First step, we need to introduce the program. So I'm going to make what's called a comment here, and that's just a note to yourself that this is a BMI calculator. Now here's what I'm going to send out to the console, and don't worry too much about the syntax. This is in Python, but just think about how we're accomplishing those steps. So that's step 1. Step 2 is to ask for the user's stats. And it's good to put additional comments in that indicate what each particular block of code does. So the more comments you put in, basically, the better. So first of all, I'm going to declare a variable here. Don't worry much about that. Again, we'll get into all the details later, but just letting you know what I'm doing. So I'm going to take a variable, and I'll call it W underscore LBS, and that'll be the weight in pounds. And I'm going to have Python call for user input, and the prompt is going to be what is your body weight in pounds? And I'm going to do this at the end, which makes it go to the next line. Just a little formatting thing, makes it look nicer. So now I have this variable is going to hold the information for me, and that's going to be an integer, and it's going to be whatever the user put in for their body weight in pounds. All right, now we need to get the height in inches. And we're going to use this same syntax. You'll see me do a lot of copy and pasting because no sense reinventing the wheel. So what is your height in inches? And we're going to have these variables that will do that. Now, if we go to our next step, it was to convert those to metric. So I'm going to take the weight in pounds, and I'm going to change it to weight. So let's do weight in kilograms equals, and kilograms, 1 kilogram is 2.204 pounds. So in order to get that weight from the pounds, I need to divide the pounds by 2.204. So the weight in kilograms is going to be the weight in pounds divided by 2.204. And we can print out to the user This will be a good bit of information. So we'll just print out what their weight is in kilograms so that they'll know in the future. And then height, we need to convert this to meters. So I don't off the top of my head know the conversion factor from inches to meters, but let's look it up. Okay, so it's 0.0254. So we got H in inches. Well, actually, let's do it this way. Height in meters equals the height in inches times that conversion factor. And we'll do the same printout. Okay, so this was our step 1, this was our step 2, this was our step 3. Let's move on to step 4, perform the calculation for the BMI. So, make a little note to myself here what this part of the code is doing. So remember, we need the weight, or the weight in kilograms divided by the height in meters squared. So I'm going to name this variable BMI, and I'm going to do the weight in kilograms divided by the height in meters to the second power. And the way you do that in Python is like this. I believe that will do it. So now, of course, we want to output that to the our last step was to output that to the user. So we'll print out your BMI is, and then we want to attach that variable. So okay, so that's as far as the coding steps go that we had talked about. That was me developing a plan and using a text editor. I recorded the code. Now we're going to interpret the code through the CPU, and we're going to get that output. So this is the last few stages, and this is all automatically done by the computer. So when I hit this button, it's going to send it into the interpreter, and we're going to see the output over here. This is all web-based, so this is taking place on a server computer. So this program will calculate your, and BMI is obscured, but it's there. What is your body weight in pounds? So we'll just put in some sample data. What's your height in inches? Okay, so one little boo-boo I need to do here. Big part of computer programming is this, debugging. So you'll see that and especially when you operate in different programming languages, you're going to be doing a lot of debugging. So it's telling me I didn't turn these into strings, which Python requires. Try it again. So there it gives me the information. So my weight in kilograms is this. My height in meters is this. And my BMI is this. So there's that task accomplished, and that's an example of developing a program.
Of it itself. The computer interprets it for you, feeds it into the CPU, and shows you the results. So, milestones in computer history. A lot of people know a little bit about computers, but they don't know the origins or how they came from. And there's probably a pretty good reason for that. Some of the early applications of computers were top secret. For example, in World War II, it was used to break the Enigma code the Nazis used to have secret communications. So that, of course, was a top secret exercise, and nobody really knew about it until many years later. So some of these are obfuscated. In other words, hard to look up because they were top secret at the time. So some ancient examples of computers, there were such things, but they were very rudimentary and extremely complicated. So there's something called the Antikythera device, which was fished up from the Mediterranean Sea, and they have only a small piece of it, and it's all these intricate cogs and gears, and scientists have determined that it probably was a really simple computer that was used to calculate uh, navigational uh, values if you're at sea, and things like you input the date and so forth, and it would give you some rudimentary idea of what your position was in as far as uh, latitude goes, I think. So anyway, that was really ancient, and it went way beyond what we thought the ancient Greeks would have been capable of. So ancient people had some pretty sophisticated devices that surprise you sometimes. And there are some other examples. I think Leonardo da Vinci developed some diagrams for some rudimentary computer-like devices. So there's not anything we would, look at and say, well, that's a computer in this time period, but there were things that technically met the criteria of being a computer. But the real computer science began around 1936 with this dude named von Neumann, and he created the CPU architecture that we still use today. And it's really complicated. He's, by all accounts, one of the smartest people to ever live. He's considered right up there with Einstein and some of the great geniuses of our time. So his work is kind of hard to follow for the layperson, but he laid out the structure of the central processing unit and memory and how they exchange information and process information, and it's still used to this day, which is a great testament to how great his intelligence and skill and so forth were. Okay, so in 1940, now Alan Turing, which is the guy the Turing machine is named after, is probably the father of computer science. So he wrote some papers that are considered to be the beginning of real computer science. And this guy is sort of considered the great uncle of computer science, if you will, like the rich uncle that um, supported the whole structure. But Alan Turing is considered the father of computer science. He was the guy that invented a lot of the basic premises that we use to in computer science today, like what is computable. He had a really fascinating take on it called the halting problem, which is also really complicated and difficult for the layperson to understand. But it creates a test you can use to determine if something is computable. In other words, if it can be solved by a computer program. And the first application of the Turing machine is really fascinating. So this was a vacuum tube based device. So, and all computers run on ones and zeros. They have a binary code at the CPU level. And so the vacuum tubes, they either had a vacuum or they didn't. So that's a one or a zero. Again, a lot of the details there are way beyond a layperson like myself, but um, suffice to say, it was one of the first computers that was used in to solve a real problem, and that real problem was this: the Enigma code for the Nazis. So they had a specialized typewriter that had a coding mechanism that would code the message in a way that only somebody with one of those devices could decode. And the Allies couldn't get their hands on one of those devices, so we couldn't understand the Nazis' communication. Now, I don't know how well you know World War II history, and I'm no historian, but my basic understanding of it is Hitler was very successful up until about 1943, and then thereafter he had one failure after another. One interesting coincidence is around that time, Turing deciphered the Enigma code using this device. So he broke Hitler's secret code, and then we knew what Hitler was going to do before he did it, and it gave us a huge advantage as the Allies to defeat him. Um, some interesting side notes to that story. He was trying to decipher this stack of messages, and you might have seen this if you watched The Imitation Game on Netflix. So he has this stack of messages that British intelligence is going through and trying to figure out the code. And what he needs is a key. In other words, a little bit of it that he understands, sort of like the Rosetta Stone. If you get a little bit of it, you can extrapolate the rest. But he needed that place to start, and he didn't have it. So he was actually he was a gay man, so he was only interested in other men. But at that time, that was not okay. So he had to pretend to be interested in women, and so he would go on dates with women that he wasn't really interested in, just to keep up appearances. But anyway, he was on one of those pretend dates with a lady, and the lady said something about those messages, and she mentioned that every one of them probably ended with Heil Hitler. And at that moment, Turing realized that that was his key, that was his Rosetta Stone to understand the rest of it. So he immediately broke the date off, ran to his computer, reprogrammed it to take into account the last bit of the text was almost always Heil Hitler, and he cracked the code, as I understand it, that night. So this machine is probably responsible for us winning World War II. Pretty interesting stuff. So the ENIAC, well, this is the first real computer that people knew about. The Turing machine, top secret. This one was public knowledge, and it had a memory device, an arithmetic logic unit, just like the von Neumann architecture I showed you earlier. And it was roughly the size of a room. And it had a fraction of the computing power even your phone has, a small fraction. So you can imagine a computer that takes up a whole large room is now outdone thousands of times over by a little tiny device. And that's a consequence of something called Moore's Law, which we'll talk about in a little bit. Um, so, early computer programming, how did it work? Well, typically you would have some input device, and it was often these punch cards. So, a punch card would represent a single line of code, and then a stack of these punch cards would be an entire program. And there were a lot of different languages back then. And basically every computer had its own language developed for it. There wasn't a reason to make them general because so few computers existed. Um, but one line of code would be punched out on a punch card like this, and an entire program would be a stack of those punch cards like so. And an interesting statement by a computer guy that was alive back then once on a video I watched was, if you ever want to know how big n factorial is, drop a stack of these cards. And so n factorial is how many ways you could stack a stack of n cards. And of course, if you drop them and they go everywhere, you got to figure out which one goes where. And he was pointing out what a tedious exercise that was, almost impossible task, really. Okay, so if you want to relive this ancient technique, we'll copy this link. Actually, better do it this way. And you can open it up in a browser, and it'll give you an interface where you can create those old punch cards. So just for fun, if you want, you can pause the video, go to that link, and create a punch card for fun. Okay, so here's an example of a simple Fortran program on one of those old punch cards. So the first line is program space hello, which tells the computer initiate a new program, and its name is hello. And the second line, and this is the simplest possible program, but the second line tells it to print out to the console, hello world. And then, and this should say line 3, not line 2. Let me fix that. So line 3 says end program. That tells it terminate the current program. So this is an example of a simple program on these old punch card style computers. All right, so moving into the next era of computers, in the late 70s and early 80s, computers first became available at a price some people could afford. They were still, you weren't going to find one in a lower class person's home at that time, but a lot of wealthier people had these home computers. And they were, for the first time, designed for general users, not for computer scientists. So the first languages that were really easier to understand became popular. Like BASIC was probably the most common one at that time. Um, but this is an example of one, the old IBM PC. Of course, you also had the early Apple computers and some other competing computers, but these were the most common. Followed, well, actually, Apple was probably a little more common in the late 70s and early 80s. and then PCs became more common in somewhere around the mid 80s. So this would be an example of a program in that era. So you would have a line of basic code, and don't worry about the syntax, because the syntax for every language is going to be different. And if you're not going to use a language, there's no point in worrying too much about it. We're not going to use basic as we go through the course here, but I just wanted to show you an example of what a basic program would look like in the early 80s. This is a Commodore 64 screen, and we've wrote a little code here, and this actually does what you saw earlier. Let me bring that back up. So it creates this repeating maze program where it just goes over and over and over. All right. Oh, skipped ahead. So yeah, these two lines. This first line tells it to pick a random character from a character set and print it. And then the second line, line 20, tells it to go back to the previous line. So it's an infinite loop where it prints out a random character, and those characters combine to create that maze you saw. And a line of code is just one of the single lines. The entire program is all the lines together, which in this case is only two, but some basic programs were thousands of lines. We were really inhibited back then by memory, though, so you couldn't even come close to what we can do today. 64K of memory. That's ludicrous by today's standards. We have millions of times that amount in modern computers.
Okay, so the most common computer in this area was the Commodore 64, and it was totally created with the programmer in mind. Almost everybody that owned one of these also wrote their own programs to one degree or another. It was very user-friendly. The BASIC that came with it, it came with a huge instruction booklet that was really thick and had a lot of programming information in it. Basically taught you how to program from scratch. Computers don't come with that anymore, so that's kind of a bygone thing. But Commodore 64s were super common, totally easy to program with, and everybody that had one of these knew how to write a few simple programs. And often, if you got a magazine back in the old days, it would have these games in it, and it would give you the actual code, and then you would go to your computer and you would type in this code, and at the end you'd have a fully functional game. You could also save it to physical media, and the most common physical media back then was the 5.5-inch floppy. If you guys are really old like me, you'll remember those were the big floppy disks. And then later the 3.5 hard floppies, the smaller ones, were more common. And then of course we went to USB drives and CDs and so on. And floppy disks are totally a thing of the past. But back in the old days you could have games on disks. But more often you would just get the text for the game and you would have to type it in. And man, oh man, if you got to halfway through this and you had one little error, then the game wouldn't work and you'd have to go back and try to debug and figure it out. And it was a great exercise for kids because you learned all this programming by accident when you're putting it in. And if you're going to get it to function, you had to be able to tell if it was exactly right or not. So there was a lot of coding knowledge and learning that took place when you would do that. And there are tons of these. So yeah, computer magazines, but not just computer magazines, like textbooks, math textbooks. Magazines like Mad magazine would have computer programs in it. I can remember one that when I was a kid, it was Alfred E. Newman, the kid with the missing tooth on the front of those old magazines. If you put it in just right, his face would pop up, and I spent hours doing that. That was the result. Anyway, so here's like a super basic program that almost anybody can remember, and it's pretty fun if you ever encounter a basic system like this. So you have to name your lines, and they have to be, it will process them in ascending order, so you want each one to be bigger than the previous number. It's conventional to start with 10. You don't have to, but most people started with 10 and then went to 20 and 30 and 40 and so on. The reason why they did that was so you'd have room to add something in between if you decided to. But you're just going to tell it to print something here, and we'll print programming is awesome. And if you ever use one of these, be careful because the keyboards don't always map out exactly the way you'd expect them to. And we'll add a little counter here. So actually, let me go back to 05. We'll say set a variable count equal to 0. And then at 15, we'll print and 20, we'll say count. I think that'll work. So here I'm telling it to go back to 10. This is an infinite loop, not good coding, and you don't want to create one that goes on and on forever, but I'm doing it on purpose here for fun. So it's going to say programming is awesome, and then it's going to tell you how many times it has said it. And this will literally go on forever until the computer fails, or you can hit the escape button and break it. So I think it's list. Yeah, brings that. So that list shows you what program is currently stored in memory. And these old computers, they were so much fun, and so many people used them as a great learning tool. You can get a really nice little Commodore 64 emulator machine, Commodore 64 Mini, I believe it's called, and it just plugs right into your monitor or TV, and it works like an old Commodore. I think those are about $30 if you have an interest in this nostalgic old stuff. All right.
In modern computers. So in the 80s, Apple, as I said, Apple sort of controlled the market in the very early 80s and late 70s with the Apple IIe. I don't know if you guys are my age, you probably remember seeing those in school and so on. But in the mid 80s, Apple came out with Macintosh, which was kind of a huge flop, and it allowed the IBM PC to take over the personal computer market. Um, so this was a really high performing computer for its time, the Macintosh, but was super pricey and buggy, so difficult for a lay person to use, and it didn't sell very well. Had a really famous commercial with the chariots of fire playing in the background and so on. That's an interesting video. If you want to check it out on YouTube, it gives you some insight into that era. Okay, so Microsoft launches Windows in 1985. So Bill Gates, and some interesting things about Bill Gates. If you ever read a book called Outliers, it basically looks at cases of people that are pretty exceptional and what made them exceptional. And one of the people that was discussed in that book was Bill Gates. And the book posits that 10,000 hours is the key to success in something. So if you have 10,000 hours of practice in a given thing, you're going to be a master of that thing. That's the basic idea. So Bill Gates um, went to one of the only high schools in America during his time, which was late 50s, early 60s, I think, that had a computer for the students to use, a big mainframe computer. And he also got unlimited time on it, including after school hours. So this dude had nearly 10,000 hours of practice programming a computer before most people had even seen one or even knew what they were. So he had a huge advantage in the software development market, and he created Windows, which, as you know now, is the total standard for almost every computer. Apple still has a share of the market, but it's a small share. Windows is the vast majority of computer operating systems on this planet right now. Um, so in the late 80s, the web first came to be. Now, the internet wasn't in any form we would consider modern until about the mid 90s, but a few scattered websites existed in the late 80s, and it was actually derived from the DARPANet, I believe it was called. It was a military intelligence network, which was based in America. But here, a British scientist created one of the first websites through CERN. And so the web was born, and people didn't realize nobody could have imagined what that would turn into, how integral it is to our daily lives at this point. So back then, you know, computer programming was obscure and unusual. Not many people did it. Not many people knew about it. But the web propagated the use of computers and motivated, grandmas to buy computers so they could email their grandchildren. A whole other segments of people began to buy computers because the internet was such a useful tool. Business people and so on, people that had not considered buying one previously. So the internet allowed computers and computer programming to become way more mainstream than it ever was before. Okay, so in the 2000s, you had broadband internet, which allowed not just little simple websites, but streaming video and games that were played in real time over the internet to be viable, and all sorts of other things to become more possible. Because I don't know how many of you guys were alive in the 90s or had to use a computer in the 90s, but I can remember having to download, just a few megabytes, and I would click on it and leave it running overnight because the bandwidth was so poor back on those old dial-up connections. I'm sure you've heard that strange sound the modems used to make when they would connect through your phone line. Excuse me. And that was our reality. You would click on something and you would go make yourself a sandwich because it's going to take a while before that website loads. Nowadays, everything's almost instant. And for those of you guys that never used the internet back in the 90s, it would be hard for you to believe how slow it was back then. So broadband internet made the internet so much more useful, able to do so many more things. All right, connected living. So today's homes are rapidly transforming into spaces where traditional computers dovetail alongside newer pieces of technology. What they mean by that is your TV has a computer in it, your refrigerator has a computer in it, your washing machine has a computer in it if you've got a newer high-end model. All these things now are smart. In other words, they have built-in computers that help them accomplish their task or give them additional functionality. Like if you have one of those fancy new ovens, you can turn it on and preheat it while you're on the way home so that you can stick your food in and immediately begin cooking it. If you have a smart dishwasher, you can have it turn on at a certain time and turn off at a certain time so it's not disturbing you or whatever. Your TV, you can say, like Alexa, tune to HGTV, and your Alexa will communicate with the computer in your TV if you've got a new smart TV, and it will accomplish that task, which is pretty amazing considering um, where we started with computers. All right, and then one of the biggest innovations is smartphones. And this is another one that kind of came out of nowhere. Like cell phones had been around in the 90s and uh, early 2000s. So we had cell phones, but they were just a phone. And they also had text functionality. So that was new and cool. But nobody could have really predicted how important smartphones would become when compared to just a regular phone. So um, you now have a device in your pocket that can do everything and more that a high-end computer would have done 20 years ago. So right in your pocket, you've got an office, you've got a dictation device, you've got something that you can take pictures with and record video. You can send an email or a text or a video to anyone, anywhere, anytime. It's just unbelievable what cell phones can accomplish. And okay, so starting with the next video, we're going to discuss the nuts and bolts of those things and what makes them work. How do they do the things they do? Anyway, I'll see you next time. Thank you guys.